Welcome to Through the Lens, a series dedicated to reveal the people behind today's breakthrough in optics. For the first season, I'll be sitting down with fellow members of the optics department of FEMTO-ST Institute in Besançon. We'll talk about their research, what motivates them, and their personal journeys. Come along as we explore the human story driving photonics forward. So I'm here today with Magdalena Marciniak. Thank you so much for accepting our invitation for this interview.
Thanks for inviting me.
Yes, my pleasure. So you are visiting research from Poland, from the University of Łódź,
Yes.
and you defended with distinction, congratulations, in 2022. And now you are a postdoctoral researcher in the same university.
Exactly. Okay. Yes, in 2 weeks it will be like 3rd year anniversary of my events.
Nice.
Yeah, same place.
Yes, it does. Can you, okay, so this is the broad lines. Can you introduce yourself a little bit more about your general interest and how did you arrive here, basically?
Okay, so in Poland during my PhD, I was focusing on subwavelength grating and what we can do with them, especially in semiconductor lasers field. And since my group in Poland is mostly dedicated to semiconductor lasers itself, it was mostly modeling. Now it's also characterization. We built basically from nothing experimental laboratorium for characterization in recent years. So now my work is more lab, not computer simulation anymore. And now I'm not that much focused on gratings. I work with semiconductor lasers, VCSELs, which are very promising devices and which now they are very popular and there's huge boom in VCSELs market. And this is actually what brought me here.
Okay, nice, great. Okay, yeah. And I love to know about when I interview people, what was the thing that drew them into physics? So do you have a person or a topic, or like how did you end up? Because it's not so common for people in general, and it seems sometimes unachievable for a reason that I don't see. But what was your reason to come into physics?
I think I was really lucky with my teachers in primary and in high school. And yeah, I've never found physics like something which I should be afraid of. It was always very interesting and I was waiting for next classes. So yeah, at some point when I had to decide what to study at university, I was thinking about plenty different possibilities, and all of them were somehow connected to STEM, to engineering, to science. But then I realized that I like pure physics itself, and maybe I shouldn't be looking for something very specific, just focus on fundamental science, and that's what I did.
Okay, pretty nice. And so it was kind of an early interest, and then it developed into doctoral studies, right? Where you studied monolithic subwavelength grating.
Yes, exactly.
Okay, can you explain me how did it start from physics to subwavelength grating?
Okay, so actually, when I was in high school, and we had this very nice teacher of physics. She was always telling us that what we are doing in high school, it's basically introduction to physics. So very ground level, right? And one day, it was already last year, she told us, okay, today we are starting introduction to physics. So I had this feeling that something big is happening. And this is where we started talking about optics, about Maxwell equations, and about light. So from that moment, I knew that this is the most interesting part of physics for me. And also, these were classes I liked the most during studies. So I was looking for my diploma, like bachelor and then master thesis in this area. And then the group which I work with now was interested in this subject. So my future supervisor suggested this topic and I jumped into it.
Okay. So it was a relatively smooth path to it.
Yes, yes.
Okay. What I like about your research path as well was that you have done quite some research visits. So I've seen that you've went to Germany and also Spain, and now you are in France. I'd like to ask you how those international experience shaped your scientific approach.
I think it was crucial to be in this place which I am now. So if it's about Berlin, it was beginning of my PhD studies or middle part of this. And it was really nice because, well, in Poland back then we could only do numerical calculations. And then in Berlin, I had real opportunity to fabricate in clean room things which I was designing during my thesis. So then it was, something really nice to present at the end because I designed something, I fabricated that, and then some other people from Warsaw, they could do some measurements, and I could present like full broad project, not only some small part. So that was really nice. And also I learned how to work in clean room and how complicated and multi-step procedure is fabrication of semiconductor devices. So this was really nice, and this was very nice adventure and opportunity to learn. And then Spain was something totally different because it was I went to Spain just before my defense, but when my thesis were submitted, and it was a jump to totally another topic. So of course it was about semiconductor lasers, but it was about dynamic of these lasers, and it was work in measurement lab with which I had almost no experience. So I had to learn a lot. Also, it was topic which was not exactly main focus of the group I was visiting. So I had to learn how to work in a lab, but also how to work by myself. And well, that was tough at some moments, but I think it profits after all. And also I could see people, PhD students from different groups, from different countries. With Berlin, it was not that many interaction. And I could see how independent these people are. I mean, there were like second, third year of their PhD studies, and they were digging into publications and exchanging ideas with each other and proposing some new projects, some new ideas. And I thought like, okay, I'm not that independent. Like I have to like reevaluate something and maybe try to be more proactive. So it gave me a lot to think and to change how I want to do science by myself. And I think it was from this point of view very, very important experience.
Yes, yes, it's true. I also have the feeling every visit I did internationally, it was a very different way, or the very different dynamics inside the group, and every time I had something to learn about it. For example, it was from the way they do their weekly meetings to the way they organize labs, or like very simple things, but that simplify your life as a researcher. And from what I gathered, you seem to say that in Berlin you were inspired about their independence as student, right?
More in Berlin, like I was mostly inspired about like connecting everything together, right?
Okay.
Like theory and designing step, and then fabrication, and then measurement, like bringing all sides of the same like the same devices, the same lasers or grating together. And it was really cool because, well, I was calculating, right? So I was designing these gratings to make them highly reflective mirrors, but also I did some calculations just to design structure of semiconductor laser. And when you are doing this in computer software, you can design it with precision of angstroms, right?
Okay.
It can be whatever you want to type in computer, and it always works. And also you can like investigate what happens if we shift something for 2 nanometers, and is it crucial or not. And then you go to lab, to clean room, you fabricate device, and you realize that you don't have control like this, that it's not that nice and smooth like in your computer, that there are some I don't know, like some struggles, some mess, some errors from experiments, some inaccuracies. And well, it's just how do we have to deal with this. So it was like more like it was something new, and it was a huge discovery that real world is something different than what I was doing in my computer. And this main inspiration from Spain was more like a work organization and personal level.
Okay. Were you able to bring back some technologies from your trips?
So from Berlin, we brought some gratings, which I fabricated, and then we could measure them and publish some results. Also, then in Berlin, we were doing some VCSELs, some semiconductor lasers, and we did, because I was there with another colleague from my group, who is also postdoc there, who was postdoc back then, and now is also working as postdoc in our group. And we fabricated plenty of VCSELs chips.
Mm-hmm.
And still we have some of them in our lab, still investigating them. And well, some of them are here in Besançon. And also right now, we are doing measurements on these chips, which we fabricated 7-8 years ago in Berlin.
Yeah. What a nice leitmotif. Okay. So now that we talked a little bit about your path, I want to focus about more the science part of your work. Okay. So as you mentioned, your early work was more focused on monolithic high contrast grating. Sorry.
Okay.
And so basically, if I understand correctly, it's like mirror that can reflect almost all incoming light, despite being extra thin.
Exactly.
Okay, very cool. So can you explain what makes them special and a little bit of introduction on it for an audience that can range from, let's say, young student to PhD?
Okay, so basically our starting point should be laser itself or semiconductor lasers when we have active region, which is placed between 2 mirrors, right? And when we are doing this with semiconductors, then there's like, when we want to have surface emission, so we have some wafer, semiconductor wafer, and we want to have emission in from to top from the area of our wafer. Then we need mirrors in this plane, and we can do that with semiconductor materials, but the way to do that is to do so-called distributed Bragg reflectors. So we put many layers of 2 different semiconductor materials, and when they have proper thickness and proper refractive indices, when we have, I don't know, 15, 20 or more layers like this, which is stack of few micrometers, which in semiconductor devices world is quite a lot, then we can have mirror which is very highly reflective. But the problem is there is not always materials like that, right? And also when you are putting materials on top of each other, they should have the same lattice constant and same thermals, restrictions, properties, right? But also if it's laser, which is supplied by current, we would expect very low thermal and electrical resistance. And it can be very challenging in some materials. So that's problem why we don't have very nice VCSELs, which emit blue or like mid-infrared light, for example. And with gratings, we can overcome these difficulties because basically what was showed before some people before and then by us, also in my thesis, is that you can do grating which has subwavelength dimensions. So when you want to emit light of, let's say, 1 micrometer, this grating has thickness of few hundred nanometers.
Okay.
And also it's like a periodic structure with period of, I don't know, 800, something like that, also a few hundred nanometers. So it's very thin. So first of all, it's smaller structure than with this other kind of mirror. And other thing is that basically you can do this grating in any kind of material which has higher refractive index than surrounding. So yeah, it's only one material. You can grow it directly on top of VCSEL structure or on top of active region, and that's all. You have your mirror.
Mhm.
So it can be solution for some problems, and that's why it may be interesting for VCSEL technology.
Okay. Yes, I understand. And later on in your paper of ACS photonics in 2021, you showed that imperfectly edge grating can actually reach nearly 100% reflectance, which is kind of almost paradoxal because I mean you would think that geometry imperfection or anything can introduce loss, but in this case it might be an advantage. So how did you discover that this geometry could
it was surprising for us too, and basically it was just curiosity because, well, we wanted to do that. Like our first guess was rectangular cross section of gratings, so stripes which are like blocks, right? Like they're rectangulars, and then we thought, okay, but when we are fabricating this grating, sometimes it's not that perfect. Sometimes this cross section is not rectangular. There are some more smooth, rounded corners, and it's something which we have regarding to fabrication methods, and it has to be there. So we wanted to calculate the impact of some imperfections on fabrication, on reflectivity, and it happened that it was still very highly reflective, but sometimes, for example, wavelength for which we have maximum reflectivity is slightly shifted to longer or shorter wavelengths depending what change in shape we are doing. So then we realized that basically we can optimize this new shape, which is not perfect rectangular, to have maximum of reflectivity at wavelength which is interesting for us. And then we had this thought that, okay, but maybe it doesn't have to be rectangular or anywhere near to rectangular cross section. So we were investigating triangulars cross section and trapezium, and actually sometimes they are easier to fabricate because fabrication doesn't have to be that optimized. You can have trapezoid instead of rectangular, because I don't know, some anisotropy or isotropy during etching structure. And when we calculated how it works, it happened that it has broader reflectivity spectrum, which is also very nice property. So yeah, I like that paper of us very much, and I hope that for now it was only showing some idea calculations, but I would really like to be to grating topic at some point and fabricating gratings like this with different shapes. And, well, it doesn't have to be me, but I would really like to see someone realizing this idea of us.
So it was a simulation only, let's say, and the next step is is to get the experiment.
Yeah. So now it's not our main goal, focus. We are somewhere else with our research, and I'm not working with gratings, but I follow what other people are doing. I am in touch with some fabrication people, so maybe someday. Yes.
Yeah. the topic of PhD is always, or most of the time, I think dear to our heart.
Yes.
And we keep following.
Yes.
That's true. Yeah, so as you mentioned, you're not working so much anymore with grating. Your main area of focus has changed to VCSELs, which stand for vertical cavity surface emitting lasers.
Yes.
They are central in many of your projects. And so so we talked a little bit about this. If I understood correctly from you, it's, let's say, a very, how can I say, a very engineered, specialized design that is like some sort of sandwich with a layer and optimized.
Yes, exactly.
Yes, where you have a quantum well,
Yeah.
right? And I've actually seen some in the lab that you brought. It's like, let's say, a piece of glass, a wafer, a size of my hand, and on top of this we have, I don't know, maybe 50 lasers. That's correct? Or
You can have thousands of
thousands?
piece of
Wow.
semiconductor size of your hand. So
Yeah, it's pretty impressive. This is what I understood, but I would like to have the view of an expert. So can you describe them exactly? And then I will ask you, why are they so important in modern photonics?
okay, so as you said, VCSEL is vertical cavity surface emitting, which means that emission is from surface. So when we have this stack of layers, emission is in this direction instead of this.
In vertical direction.
Yes, vertical direction, exactly. So like name says. And well, it requires this stack of plenty of layers to have these mirrors I've already mentioned, to have high reflectivity, where mirrors are crucial to have laser, right? You have active region between two mirrors. And it may seem that VCSELs, because of so many layers, they are hard to fabricate. And of course, it's challenging, but actually they are cheaper than other semiconductor structures, because when we fabricate them, and we have this chip, which can be a few inches diameter, and we have thousands of devices on this chip, we don't need to cut it to have final laser, right? To test if it worked, because basically we have surface emission, so we can just apply current to every device and check if it emits light, if it's wavelength we were aiming. And because of that, because of testing, there are much cheaper, but also it means that without nothing, we can take one of them, but also we can have like 100 or 1000 or whatever. So we can have arrays, like 2D arrays of lasers, also in very easy way. And another advantages is like very low threshold current, so we don't have to apply a lot of energy to have lasing. And because of that, VCSELs have plenty of applications. So first, like main application for VCSELs, where communication, like sending signal in free space or through glass fiber. Basically, you have small semiconductor laser, which is like on, off, and you're coding information that way. So on is 1, off is 0, and then someone at the end of your fiber detects that and know what kind of information you are sending. So basically, you can send internet this way, like all the movies, streaming, whatever we are doing, right? And this was the biggest thing. So plenty, like main focus in this area of VCSELs were to optimize this, to make them more energy efficient and faster, and also to be sure that they emit only single wavelength. So there are so-called single mode devices to use them in communication. But then it was like 2 years after I started my PhD thesis. Some people decided they had this nice idea to use VCSELs in 3D mapping and 3D detection. So since then, it was iPhone X, I think. It was the first device when they put VCSELs, array of VCSELs, to recognize faces. So when you have your phone, it emits light to map your face, and you can use it to some security check, but also to have, I don't know, cat's ears and nose when you talk with friends. But since then, it was huge boom for VCSELs, and since then, this area is expanding, and it's more and more ideas, researchers, and more money, more companies interested in this. So I think that after these years, since then, basically everyone who has phone, which is not like 7-10 years old, has some VCSELs in his or her pocket.
Yeah. I mean, it's surrounding us everywhere. If it is in the phone or security, for example, in the airport, you are scanned. So it's kind of a daily device that we are not aware of.
Also some automotive devices, and it can be also, like automotive car, but also vacuum cleaner in your apartment, right? So yeah, I think most of us have some VCSELs and we use them every day.
Yes. I want to know what you are doing currently with VCSELs.
So when I was PhD student, VCSELs were mostly for communication, and I was like, okay, it's just optimization, making this slightly better, improving. It was like more engineering, industry application rather than science, right? But when we were in Berlin and we were fabricating this plenty of VCSELs, we also did some VCSELs which are not circular. So basically on this huge, or not that huge, but on this piece of semiconductor wafer, we fabricated thousands of devices, and all of them were like small cylindrical shape lasers. But we thought that, okay, let's do it not cylindrical. Let's connect two cylindrical shapes next to each other, or three. So from top, it's like clover shape, or we were investigating some different crazy ideas of VCSELs geometries. And well, basically then that was it. We measured some properties. They happened to be more energy efficient. So it was nice application. I mean, nice, not application. It was nice advantages of these devices. We had really nice paper in Optica about that. And that was it, I would say. But I wanted to investigate this topic, and well, I was like following what's going on. If someone follows, and it happened that. So I went with these lasers of different shapes to Spain just to investigate the dynamics. But at the same time, my colleague, who was fabricating lasers with me in Berlin, he went for some conference when he met Daniel Brunner. And Daniel had this idea of using VCSELs in optical computing. And what he wanted was a very big, like, multi-mode VCSELs, which no one had for him, because people wanted to have small energy efficient devices for data transmission. And then he met with my colleague Marcin, and it happened that VCSELs, which we fabricated many years ago in Berlin and which are in Marcin's drawer, are perfect for what Daniel wants to do.
Daniel in FEMTO-ST?
Yes, exactly.
And your colleague from Berlin? Okay.
Yes. So Daniel took some VCSELs from us and some other sample fabricated from another PhD student in Berlin. And well, actually, our colleague Anas did very nice research about that in his thesis, right? And now we are exploring this multi-mode weird shapes VCSELs and what is possible with, like, what we can do to use them in optical computing. And since in Poland we have nice lab for VCSEL characterization for measuring some very fundamental properties like emission spectra with high resolution and just light current voltage characteristics and so on. And here you are doing this really nice optical computing, and we can combine it together. And hopefully we design some new shapes. We came with some ideas for new shapes, for new designs, and maybe we can also fabricate them, because right now we are starting a new project in Poland, which is about new ideas for VCSEL geometries. So yeah, hopefully it will be also for optical computing.
Yes.
Here.
So it makes them the perfect tool for optical computing because of their compactness, energy efficiency, and what else? Nonlinearity, of course.
Of course.
So yes. So I see why this collaboration is working well.
Yeah, and we are just starting, right?
Yeah, but what are the bottlenecks for VCSEL if you want to use VCSEL for optical neural networks?
Well, of course, if you want some device, like some optical computer, let's say, using big words, you need something which is very stable and not for one day, but for years, right? So, of course, degradation may play some role here, and that will be the problem. And also, VCSEL is one thing, right? But as you can see, right, as you could see in laboratorium right now, VCSEL is very small, but all the other elements to make it computing information, it's still like one optical table in our laboratory. So huge challenge will be to miniaturize everything, to put it on a single chip, basically.
Yeah.
Because then we have something, and then we have some kind of optical computing chip, right?
Yeah, but I think that's a common challenge for every group. Miniaturize everything.
Yeah, of course.
Yeah, but that's what I believe is also interesting in our area, that there's so much to do still in order to make it a relevant
some
solution.
Other very cool research which people are doing here, like with printing these wave couplers, right? Yeah. Which are also on like chip scale. Like we have some ideas to do it, right? Yeah. It's not just the dream and fairy tale. Yeah, it may happen.
Yeah, well, that's what makes it interesting. So yes. Okay, I will cut that question. Now that we are done with the science, I'd like to dive in more into motivation. I have a few questions for you. The general purpose is to inspire the student. Okay. Yeah. So photonics can be very theoretical, like you have seen when you were working in Poland at first, or completely experimental, when you have discovered that later on in different lab and then back home in Poland. So which one do you prefer, and why?
I prefer lab, definitely.
So experimental.
Yes. I don't know why. Maybe it's because it's more interaction with people, so it's less lonely work. But maybe it's just my feeling and how work was organized by me in these different stages. Also, it's like more is happening around, right? In lab. Mm-hmm. I mean, also it's sometimes you have to code, you have to analyze data, you have to do measurements, you have to set up everything. I mean, it's plenty different challenges, and that I like.
Yeah. Okay. And was there during your studies or your work afterwards a failure or an experiment that didn't work and that taught you something unexpected?
For sure, there were like topics which we started, and then we decided, no, that's not the way to go further. And there are some results which I was working on for many weeks, and then I jumped to another project, and there are still, well, not in drawer, but some, I don't know where in my computer, and probably there will never be like presented, published, because it's not time for them anymore. So yes, it was not epic failures, let's say, but there were some weeks of work which was like not going anywhere, as we realized after. But I think it's normal.
Yeah, of course.
And of course, there was plenty like, let's say, small failures, right? That, I don't know, you are doing measurements and it happens that it was wrong, one element in your setup. So all the work from 1 2 weeks you have to repeat, right? Or that you are doing processing of lasers and it's like, I don't know, let's say 2 weeks work, and then at the last stage your sample is on the floor in many pieces. Because it happens in lab, and
Yes.
I think it happened to everyone who is longer than 1 year in this.
And what did you learn from it? If there is anything to learn about,
That it happens.
Okay, resilience, I guess. This is what you're saying.
Yes, I mean that's normal. That sometimes we make mistakes. That sometimes, well, there is like possibility that something will happen. It's not because of us, but right, it can be, I don't know, energy shortage in your laboratory or whatever, and nothing will be perfect. So I've learned that I'm not perfect and I can make mistakes. It was hard to accept first few times, but I think I've done this lesson. And also that, yeah, that sometimes just what happens around, it's not working for us. Sometimes it will, but not always. And also I've learned that, well, I'm not doing this like the same mistakes. I'm not repeating them, so I'm learning from them. But also I've learned that I wanted to say that if we learn from these mistakes, it's okay, because then we are not repeating them. And it may happen that also other people will be not repeating our mistakes, or we can learn from mistakes of another people. So that's important. But also I've learned that I'm doing them more often when I'm in pressure. So for example, when there's time pressure, it's somehow higher possibility that something will go wrong, right? So I think it's really good to not put too much pressure on ourselves. And sometimes we are doing that.
Yeah.
Sometimes environment does that for us, right? So I think that pressure is not helpful for us.
Mm-hmm. Yeah.
Or too much pressure.
Yeah. A little bit is always
Yeah.
maybe pushing you, but too much will push you over the
Yes.
stuff. Yeah. What role does creativity in your research play?
I would say I'm not the most creative person. So for me, it's very hard to start from the very beginning. And whatever it's about code or about experimental setup or writing paper, like I need some base to go from this point. So the beginning, starting point is always suffering for me. I'm really good at optimization. So when I have something which is more or less ready, or like there is beginning, I know what to do to go in more effective direction. So yes, I know that some creativity is necessary for this job, but also I know that it's not individual. It's like work effort, like group effort every time.
Mm-hmm.
Or most of the time. And fortunately, people I work with are much more creative than I, but I have some other, like, I don't know, I have some other advantages.
Yeah, of course.
Which, which can be also used in this process. And I think that's good that we are not the same, and together, like with our group, with many people, we can be more effective. And yeah, like optimization, but also like putting everything in some order. That's
Okay.
that's my thing.
Yeah. So More like in a collaborative way.
Yes.
Okay.
Yeah.
The last question I have for you is, so looking ahead for the future of science, what kind of discovery or technology would you like your student or the student of your student to to discover later on?
I have no idea. So for sure, I hope that we will explore this idea of weird shape pixels and different applications of them. So right now we just want to do we want to design them and fabricate and explore their properties. But I really hope that our next projects, so maybe mine, maybe projects of my future students, will be about applications of these devices. And I'm curious what directions it will go, because there is plenty of different ways and applications and possibilities there.
Thank you very much for answering my question in a very inspirational way.
Thank you.
It was a pleasure to receive you on the podcast today. And yeah, that's it. Thank you very much, Magda.
Thank you very much.